Thanks, Juan, very much for organizing this very nice workshop and having me to talk. So, I changed the title a little bit. I hope you can still see the title. I will try to write in bigger letter. The talk is about the modular flow of some boundary region can be a disentangler, and that's motivated by this question, which looks trivial, like HRT is not RT. Like, why HRT is not RT? Let me explain why I was asking this trivial question. So I will start by explaining the motivation. So we know, so if we look at time translation invariant geometry, then we can write the entropy as the RT formula. Where the entropy is given by a minimal surface, and I don't need to think about time, so I have a spatial direction. I'm minimizing the area bounding a boundary region. And in that case, this has a very natural interpretation in tensor networks, which motivated all the recent works about tensor network. So there is a correspondence to this fact in tensor networks. Where I think state living on the boundary as some as described by some tensor network, and the bulk is some internal lines that I contract to get the boundary theory, to get the corresponding state on the boundary. Then the minimal surface area corresponds to the minimal number of links I cut to separate a region A with the complement. So if you assume every link has a bound dimension, has the same bound dimension d, then the entropy of A is always smaller or equal to log d times what I call the minimal area, and the minimal area means the minimal number of links I cut. So, and then we know this is true in general tensor networks, and for particular tensor networks, for the random tensor networks, for example, we can saturate the equality. Okay, so then when you have this tensor network picture, then you like to apply it to time-dependent cases. Then when you just think of some schematic picture, then we usually think of time-dependent geometry as corresponding to some, like the tensor network itself is also evolving in time. For example, when we think about, say, an eternal black hole case, when you have a two-sided black hole, then say this corresponds to the wormhole you see in Lenny's talk. And then when you go up in time, then roughly speaking, it looks like a tensor network that's longer, but not wider. Like, so the entanglement entropy of the two sides stays the same. So you heard from Lenny's talk these discussions that this looks like a complexity grows, which means the left and right are entangled with the same entropy, but they entangled in a more complicated way. And that means like this is like a circuit which maps one side to the other. But if I really think about this representation of this as, if I really think about a tensor network like this for my state, then it will suggest to you something that's wrong, because I mean, if I literally take these kind of formulas and say take the equal sign, there was something wrong about this tensor network picture, because tensor network is always drawn on some spatial geometry, a discretized version of spatial geometry, which is a discrete graph, and that will require that you always apply this RT formula, which has different minimal surfaces that are codimension 1 in space, right? And that means different minimal surfaces will always intersect with each other. in this particular case of the black hole, it means if you think about this state later here, and then ask, okay, what are the entanglement surfaces? Then the entanglement between left and right will be given by like the horizon will be given by actually something here, right? We know in the holographic calculation, when you look at the entanglement entropy of the left with right, then it's given by the horizon, which is here. It's not in the later time, and it's something here. And on the other hand, if you look at the entanglement entropy of a different cut, which is you take the, let me draw here, you take the left side and you cut it to AB, and you take the right side, you cut it into CD. Then when you look at the entanglement entropy of BC with AD, then when time is not too late, you will get this given by the minimal surface, minimal surface like this. Right? This is in the paper of Tom Hartman and Huan. So you see this growth of the entropy of BC until time is too long, the entropy saturates to a volume law value. But before that, like when the minimal surface is given by this, then you see that the minimal surfaces bounding different regions generically lives in different spatial slices, and they don't touch each other. Right? And this is telling me that I cannot describe this by the simplest kind of tensor network where the entropy is given by the number of cuts, because you have to use different tensor network here and there. Like if you use a tensor network that reproduces this geometry correctly, then this middle part will be smaller than the black hole area, the horizon area. So that will tell you you underestimate the entanglement entropy of the other cut. So this is this is telling me why this difference between RT and HRT is very important. So when I try to describe the state with tensor networks, it tells you that the simple kind of tensor networks requires something like RT formula. So in other words, whenever the HRT surfaces bounding different regions on the boundary, whenever they don't intersect, there is no tensor network description which applies accurately. So that's the motivation why we want to make this more quantified. Although, like from the gravitational side, you may say it's easy to tell in which case RT formula applies. Right? So in which case the HRT surfaces intersect with each other. It happens when you have time reflection symmetry. But I want to ask, since we see like there is the fact that the HRT surfaces do not intersect is telling me that I cannot describe the state by some tensor network, then that's some quantum information property of the state. So I want to make this more quantified. That's the motivation of this work. And I realized that I forgot to acknowledge my collaborators. I'm sorry. So this is ongoing work with Yiming Chen and Xidong and Eiter, who is here, like Eiter Luquis and I. Is the motivation clear? Yeah.
Can you just say again which entangling surfaces are not intersecting? It's AB relative to...
Yeah, so the one for gamma AB is a circle, which is the point here, and gamma BC. Okay. Yeah. And let me draw a simpler example, which I'm going to also use. Am I going to run out of Blackboard soon? Maybe I'll draw a simpler picture here. Just to make it easier to see, we draw a single-sided case where I have only one boundary. So let's say it's just a pure ADS. Then if you consider a boundary, I can define boundary states on different boundary time slice. So I can draw a slice that's a little bit strange. That's like this, which is basically it's obtained by starting from the ordinary cut and boost the two sides to different directions. It's still space-like. Now, for this slice, the same thing happens. Like if I look at ABCD, like 4 partitions, A, B, C, D, where the boundaries are at this point. So each part is like a quarter. Then you see the same thing happens, like the gamma AB is this one, and then gamma gamma AD or BC is this, which they do not intersect with each other. So okay, so that tells me there is something different for this state compared to the state that you get by say cutting at say like this. There's some difference between these states. So the question is, how do I quantify these differences? Yeah.
If I took the view that the dual of the boundary state is the whole Wheeler-DeWitt patch, I might come to the conclusion that the tensor network should fill the space-time of the Wheeler-DeWitt patch.
That's a.
And then the point would be why are you imagining that the tensor network fills a space-like slice, and if so, which space-like slice?
Yeah, we don't have to, but we have concrete tensor networks where we can show the entropy is equal to the minimal surface in that spatial slice. Well, I don't have if I think about tensor network as due to the whole Wheeler-DeWitt patch, I don't have an explicit like tensor network I can write down and prove the entropy is given by the extremal surface. That's the reason. I mean, actually, I have some proposal like about that, but it's not explicitly writing down the wave function. So yeah, but I mean, there's some generalization to space-time, but it's talking about partition function instead of wave function. So if I really want to write down a wave function like this, then yeah, you could argue that this graph do not correspond to a particular spatial slice, but as long as it's always a graph.
It's supposed to describe a boundary wave function.
Yeah, it's a wave function.
Why the lines inside the graph have to be thought of as filling a spatial surface.
Yeah, they don't have to correspond to any spatial surface in the geometry, but the point is that as long as this graph is fixed, it still have this property that when I consider 2 regions, the minimal surface always intersect in the graph sense. So so there is still something particular, and the HRT is suggesting me this is not always true for a general state. This intersecting property. Okay, so now let me first just describe what is our proposal. So we make a conjecture of how to quantify this non-intersection of HRT and how that's related to modular flow. So there is a proposal. There's something in the bulk correspond to something on the boundary, and then we will give some evidences of this conjecture. Okay, so the conjecture involves something in the bulk, and that's mapped to something that's some quantum information property of the boundary. So at the bulk side, the quantity I want to consider, or maybe I just show it here. Okay. Let me just show it here. The quantity I want to consider for a given 4 partition of the boundary is let's first find the minimal surface bounding AB. So find the gamma AB. And then we define a restricted extremal surface bounding BC, which is defined by an extremal surface that's forced to cross with gamma AB. So let's call it gamma tilde BC. And gamma tilde BC is defined as something like this. And more precisely, you could say I'm doing a max min with a restriction. So we generalize Aaron's max min procedure, and we say we are choosing spatial, like codimension 1 spatial surfaces sigma bounding this boundary, and then minimizing the area of some curve that's bounding the region BC. And then I max over the choice of sigma, except a constraint that the sigma must include the gamma AB. So gamma AB lives in the sigma. So this gives you basically like in the 3D bulk case, it gives you a joint of two geodesics like this, and then you move this point to minimize the sum. So okay, so this is the proposed area. So it's the area of the gamma tilde BC, which is defined. Well, it's something that you define by first identifying gamma AB, and then you do the restricted minimization. So as you see from the picture, generally you get an area that's smaller or equal to the actual entropy. So let's divide by 4G Newton, then define that as a constrained entropy. We didn't find I wasn't very comfortable with this name, but we didn't find a better name. Yeah.
Is that maximum the definition, or was there some other definition?
That's the definition in the bulk. Yeah.
Okay.
So that's the quantity is defined in this way in the bulk, and then
is it extremal away from? Is gamma tilde extremal away from where it intersects gamma, AB, or whatever?
Yes. So well, it means like because I'm going over all the sigmas that include gamma. So it's extremal like here. In 3D, we could just say fix a point here, find the extremal geodesic, and find another geodesic, and then move around to minimize the sum. I guess in higher dimensions, you can also say that except this point is a codimension 3 region on the gamma AB. But so I think this is a general way to define it. I'm doing the max min, except I require to use a sigma that includes gamma AB. So that other than this intersection.
A sigma on which gamma AB is minimal, or can it be an
No. It's just, as long as it includes gamma AB. You just you don't. So that requirement doesn't allow you to find the actual geodesic bounding this region, but it finds the restricted spatial minimal surface in that restricted slice.
So something similar that Tadashi Takanagi and somebody he was working with did recently, where he was anchoring extremal surface.
Yeah. So.
I think he said he proposed it was related to this antenna purification.
Yes, right. I'm going to comment on the relation. Apparently, yeah, it's very similar, except that in Tadashi's case, it's like you only have 1/2 of this, like from here to here, and you are minimizing that. Here, I'm minimizing the sum of the two. So generically, there is some inequality relating this to the entanglement purification. They have to touch in the same place, yeah. Okay, good. So if the definition of this quantity is clear, then constrained entropy. Then our proposal or our conjecture is this is due to some quantity that you can calculate purely from the boundary wave function. And let me describe what is this quantity. So you take the state of let's take the state defined on that take the state defined on that time slice. And because I'm only going to use the 3 regions ABC, so let me just write rho ABC. So I have rho ABC, the state of the ABC, and then I do a modular flow of AB, which means I'm doing kind of a real-time evolution for the modular Hamiltonian of AB. So something like this. Let's say like this. So now I get this is a new state. So this is a new state of ABC that's parameterized by S. And then I can calculate the entropy of BC in that state. So I can calculate the entropy of BC for sigma, and then minimize for the modular parameter S. So the proposal is this is equal to that. So that's the conjecture.
Supposed to be true for general geometries or just when it's sort of the Rindberg case?
Well, in that case, it's trivially true. So the proposal is generally true. I'm going to discuss some different evidences, which at least suggest it's not only true in this kind of trivial cases. Yeah, but of course, it's clearly you can easily see it's. I'm going to explain, but you can easily see it's true in that case. Okay, so this quantity is. This is why I'm calling. In the title, I'm saying the modular flow as like a disentangler. Because so what does this quantity mean? It's like take your state, which contains A, B, C, D, although I didn't use D. But so this quantity, then now if you calculate the SBC, you get some entropy, right? But now when you do the modular flow, it's like you are applying some unitary gate, which is this rho AB to the power IS. That modular flow. So if you write rho AB as e to the ik, then this is like just an ordinary time evolution. And in that particular geometry case, where the modular Hamiltonian is just that Lorentz boost, then of course this is just boosting the regime. But so in general, but this definition is independent from any detail, like whether the modular flow is local, whether modular Hamiltonian is local. So for any state, I can define rho AB and I can do this. So the picture is like I'm applying this unitary gate, which is determined by the state itself. I'm applying the unitary gate with a parameter to this state. And then you calculate the entropy of BC after you do that. And generically, the entropy may go up or down. But so the proposal is whenever you have these HRT services that do not intersect, you can actually find an S that's non-zero, which makes the entropy go down. And that gives you this minimized entropy that's this constrained entropy, which as we know here is generally smaller or equal to the actual entropy. So like, and for the case of like time translation symmetry, then when all the HRT surfaces intersect, then we expect the minimal happens at S equal to 0. It means you can do this evolution, but it's always going to make the entropy bigger. That in that case, the modular flow is not a disentangler. Since the definition was a little long, is it clear what is the bulk quantity and boundary quantity?
So is there some special meaning to the S which minimizes that?
I'm going to describe what happens when the modular of Hamiltonian is local. In that case, there is clearly a meaning. More generally, I don't know. Maybe I will come here. Okay, yeah.
Since S tilde BC is not the entanglement entropy, in what sense this is a disentanglement?
It means the fact that so the boundary calculation is you look at this one parameter family of sigma and you look at the minimum of this entropy, and that's what I call SBC tilt. And it's a disentangler because generically the minimization gives you some entropy that's smaller than the original entropy. So that means that applying this gate decreases the entropy between B and C. Like originally in the state, there is already some entanglement. If you just apply some general unitary that doesn't know anything about the state, generically the entropy will go up. Will be like something here plus something here. But if you apply something very special, then you may cancel some entanglement that was already in the state. Yeah, so it's not completely disentangling, but it's going to the disentangling direction. And it will become clear in the local case why that's happening. Yeah.
Just have a question on nomenclature. Normally, Disentangler, wouldn't that be something that taxon B and C? Oh, no, sorry, I got a mistake. Sorry.
Yeah, because I'm looking at BC, so there's no hope to disentangle if you apply something on BC. Yes. It's similar to what we call disentangler in Mera. Yes. Okay, so let's look at so now we want to look at the evidence why we made this conjecture. the first one is when the modular flow is local. When the modular flow is local, and more specifically, I mean when there is a killing vector, like that case I'm drawing there. Like when there is a killing vector in the that does the modular flow. So this is actually some integration of energy momentum tensor along some killing vector. So if that happens, then clearly this sigma is just the state on a different slice you obtain by doing this by moving the boundary on that direction. So in that vacuum case, you start from a state like this, and then the modular flow will move you to other states like this, all the way. Like when S goes from plus infinity to minus infinity, it goes all the way from these two boundaries of the entanglement wedge. So it's doing this motion, and then for every parameter S, the sigma is defined on this surface, and then the entropy of BC in that S at that modular time is given by the minimal surface that's like this. So you start from here, which is S equal to 0, and then you go down. And then, of course, I'm just moving the endpoint of the interval. So there will be a point where this red curve crosses the green curve, goes from up to down, and that's the parameter S where the minimum occurs.
So I'm trying to understand this argument, and the details are clear to me in the case where you not only have a killing field, but you also have time reflection symmetry. Is it sufficient to just have a killing field without time reflection symmetry?
No, I think I only need a killing field. I mean, I'm not sure because the state is defined on this slice, so there's no time reflection symmetry. I mean the state here, the state is not time reflection invariant. Right. If it is, then you can prove that S equal to 0 is always a local, at least as local extrema. So this phenomenon doesn't happen. Like I mean, if you have a if the boundary slice itself preserves reflection symmetry, then the minimal surfaces already cross each other. Yeah. So we start from somewhere here, and then you can do the modular flow, and then the point is that this S tilde is defined in a way that clearly is independent from the modular flow. Like when you do the modular flow, like if you start from sigma and define S tilde for sigma, it's the same for rho because I'm minimizing in S. So generically, the entropy is bigger or equal to that line, but when these two cross each other, then it should be equal, because that's where going away from that surface do not gain you more, do not give you an increase of entropy. Yeah.
I also don't understand what Don is asking about. How do you see that this straight line has equal area to the other line that you drew on the other board?
So the argument is if you do this modular flow and follow how that kinked line evolves, then basically it's start from here, and then it's doing something like this, right? But the length doesn't change. This is just a boost of the same curve. So it's this, and then the statement is that when you reach the point where the actual geodesic cross the green geodesic, cross the gamma AB, then that must be the same as the joint of the two orange curves. Because the orange curve is defined as restricted extremization, but when you have that crossing point, that means releasing that constraint do not give you non-zero derivative. Yeah.
I didn't understand why the intersection point doesn't move.
Oh, the intersection point, because because when you so the restricted extremization is done on spatial slices that include this line, which separates the bulk into two parts. So the extremization of this doesn't really depend on that.
Why not? I mean, they still have to connect, right?
Yeah, but so okay. So I mean, in this particular case, it's because the modular flow is a symmetry in this case. I don't think you need a spatial reflection symmetry. You just need the modular flow itself to be a symmetry.
Well, in this case, there is a in this case, you don't have to move it through there because there is a spatial reflection symmetry between BC and AG.
That's actually assumption.
No, it's not an assumption. It's just this example.
No, but that's a special case, right? I don't have to take BC to be half system. Because I mean, the point is that this entanglement wedge has a symmetry, which is given by the modular flow when the modular flow is local. And so a extremal surface here after the modular flow is still extremal, and they have the same length. So if you move this point and you already find the extremal point for this sum, after the modular flow, it's the same point which gives you the extremal, because they are related by symmetry. Okay, so in this case. Yeah, so in general, I mean, this is a vacuum case. In general, the argument is just, as long as the modular flow is a local, then you can just follow how is this boundary point is flowing. Then, I mean, when you reach like the upper tip of the extremal of the entanglement wedge, you always get something that's on top of this green thing, and then when you go to the bottom, you get something below it. So there is always some point where they cross, and at the crossing point. The entropy of sigma, at crossing point, the restricted minimization is the same. The restricted extremization is the same as the unrestricted one, and that gives you that tells you that the minimal value of this entropy is equal to that surface. And the same argument applies to the black hole case, where if you are you're talking about this state, and then the modular flow basically will pick this point where you just basically, in that case, the modular flow is the same as time evolution of one side, and you're just undoing the time evolution to reduce the entanglement entropy of BC. So it's clear in that case it's a disentangler. In general, you may not do as good as that case where you completely undone the time evolution, but you're trying to do part of that job. And another piece of evidence which also help suggest that this may not be restricted to the case of local modular flow. Another piece of evidence is from considering 2 plus 1D bulk. Let's assume it's 2 plus 1D. But not assuming its modular flow is local. So in that case, I want to apply some results of Tom Faulkner and Eiter. Where they write down some formula about modular if you do modular zero modes, then it corresponds to some operators living on the minimals, living on the HRT surface, because by definition things there are modular flow invariant. But to use that formula, let's first write some kind of Rényi version of this conjecture, and then take the von Neumann limit. So the Rényi version is we take that sigma ABC, and then we look at some trace of sigma to power k. So this is like e to the Rényi entropies. And then let's integrate this over the modular parameter s. We should integrate over all the real number S. We can do that by taking a cutoff. Let's say take some cutoff and take the cutoff to infinity. Okay, so so let's define this quantity as zk. So it's kind of like a modular average, the exponential of exponential of kth Rényi entropy, and then we want to go back to the von Neumann limit, so we can define the standard thing. Let's define sk So this is just like going from a partition function to the thermal entropy. It's not the standard Rényi entropy, but it's like the Qidong's version of the Rényi entropy. But it also approaches the von Neumann when you take k goes to 1. If you don't have this modular average, you just get the von Neumann entropy of this. But here, like for a finite Rényi index, this is an average over different modular parameters rather than the extremization. But if you consider first taking the large n limit, and the entropy is scaling with entropy is growing with n. So if you take the large n limit first, then this integration will be dominant by the minimal S parameter. And then when you take this limit, you when k goes to 1, we get, sorry, can you see here? Sorry, I mean sigma BC here, because I want to look at the entropy of BC region. Yeah. Sigma BC means the sigma ABC, and then you trace over A. So we are doing sigma BC here, and then the constrained entropy S tilde BC is the limit k goes to 1 limit of SK. So okay, so this is just saying in the large n limit, this is strongly peaked. So when we integrate over S, it's dominant by the minimal. So it's just a trick to relate the modular average, which shows up in their formulas, relate the modular average to the von Neumann entropy. Because this modular flow, I'm going to relate this. I mean, the way we want to relate to the restricted geodetic surface is by introducing operators on the extremal surface, and that's only done for like operators. So Rényis are like a correlation function of a two-point function of operators in the replicated theory. So we cannot write that for von Neumann. Yeah, you should take a t goes to infinity. Yeah, and because this quantity strongly peaked around some S minimum, so taking t goes to infinity doesn't give you a divergence. That's the argument. And yeah, so the point is that you can write Rényi entropies as a correlation function in the 2+1 case. You can write Rényi entropies as a two-point function of twist operators in k copies of the theory. So if you take sigma ABC to k copies, just independent k copies, then you can introduce these pairs of twist operators. Let's say I'm going to write them like this. And these twist operators are defined by like cyclic permutation between different replicas. So it means that if you look at the A, B, C, then you take multiple copies, and then you are cyclic permuting between the different copies by these operators. and xy means the end point of the regions. So by xy I mean the end point of the regions. Okay. So then because sigma is obtained by the modular flow, so this is the same as calculating the modular flow operator in the original density matrix. So it's something like that. Like I'm flowing, well, I don't need to write a 0 there. The modular flow do not even apply to that. So there's a modular flow of AB, which is conjugating that operator. Right, so I have this xk, which is being applied by k copies of the modular flow. And then now we can apply this Faulkner-Lukowitz result to where they say if you integrate over S, then you are left with things that are invariant under modular transformation. And these are things that live on the extremal surface. Generically, you can expand the operator into operators living in the entanglement wedge, but when you integrate over S, you only get operators living on the geodesic surface. So that means we can expand this operator using its correlators with something living on the geodesic, something like this, where this Z lives on gamma AB. So you are looking at, say, this is the operators in the k copies of series. So you have this operator here, and then you have some operator living on this geodesic, and then some. So, sorry, not that yet. So then this correlation function determines the coefficient of that operator. But now with that, let me just write down this part. We can so now you expand the operators on the geodesic, then you can write this this two-point function of twist operators to multiplication of two correlation functions. So you see it's like there is a geodesic, and then then this two-point function. Now, after the average over modular flow is mediated by something in the middle, which is forced to live on that geodesic. And then, so in the large N limit, these operators are heavy. So we can approximate this two-point function by exponential of the geodesic distance. So you are basically integrating over something like delta times a sum over two distances. And this is scaling with n. This is large in large N limit. So this is approximate. This is when you, and this depends on k. So when you take the saddle point approximation and then take derivative over k, in the end you just get that the S tilde is equal to the minimum of this sum times the standard coefficient. well, this coefficient should be the central charge in the CFT. Is this clear? So I want to emphasize the point is that this doesn't require the modular flow to be local. So in this case, I don't know exactly what the minimal S corresponds to. But even if the modular flow is not local, as long as you can still expand the operators using the operators on the minimal surface, you see that this restricted entropy, this constrained entropy, is still given by that restricted minimal surface. So now, basically, we have semi-proof for the case where you have either a local modular flow or you have 2 plus 1D. So the only case that's actually a conjecture is the case that's higher than 2 plus 1D and you don't have a local modular flow.
Sorry, but even in 2 plus 1, it's just for single intervals?
We have been mainly thinking of single intervals. For multiple intervals, naively, I expect it also works, but I haven't really thought about that more carefully. Have you thought? So I think the formula, this formula still applies when you have, when you have like multiple interval. When you have this, and then you can still expand it to that. But I just don't know how to draw the whole thing in that case. So so far the thing it's the single interval case where I understand how to make the statement more precise. As far as my understanding is, their formula was restricted to 2 plus 1. I don't know why that was the case.
I mean, I would say because in 2 plus 1 the twist operators are local operators, and we like the formula for local operators. I don't know how to write the twist operator in higher dimension in terms of an RT operator.
So in higher dimensions, the twist operator will be defined on boundary of the regions.
Right?
Which is it's defined on the surface, and then you will need some generalization of such formulas, where phi will not be local, I guess.
You can have correlators of defect operators with things that are on the surface.
So if you have a generalization of this formula, then it should still work. But then I have to sum over the phis that lives on all codimension 3 surfaces of living on that gamma AB.
How do you go from modular integral of product of 2 twist operators to 1 twist operator?
To 1?
Yeah, so there.
No. This is just because only this one contains S. So I'm just doing the integration over S for that operator. This is the operator, and this is also an operator. Then we put that back here. That's how you get the other correlator between this and XY. So you get 2 correlators here. You get that by, this part is like the modular flow, the XK, and then correlator with that.
I have one question. So if the formulas you are writing, in principle, should make sense also. The formula in the field theory makes sense to all orders. Exactly in N.
Yeah.
So in the bug, one is tempted then to say, well, the next order in the 1 over N expansion would be some kind of entanglement entropy in that.
I think I don't have a simple guess. The entanglement entropy of it doesn't seem to work because, like BC has an entanglement wedge which contains AD. So the bulk, if you look at 1 over N corrections, then for the
I was worried that you specify the entanglement entropy of the region that is to the front of the blackboard of the line you wrote.
Yeah.
But it has a kink, so I was wondering whether that gives rise to divergence.
Well, if you define the bulk entanglement entropy for this, I think it will be the same as the entanglement. You have an ordinary entanglement wedge. There is a kink, but the entanglement wedge is something completely normal. But that's something that's not going to. I don't think that's the right because there is no constraint in that bulk entropy.
Well, you take the surface that goes between BC and the boundary and the line you wrote, right? That's a bulk surface.
This one.
Yeah, the
Yeah.
BC, so
Yeah.
that's a bulk surface, and then you compute the bulk entanglement entropy of that.
Yeah.
I was just
Yeah, you could do that.
So
Yeah. Yeah, I think this integration formula is suggesting it may not be that. I mean, because if you write it as this integration over S rather than minimization, then the leading term in N will be dominated by the saddle point. Then the subleading term will be like an average. Yeah, so it may be a little more subtle. Also, yeah, also that thing is well defined. Okay, I guess you didn't require modular flow to be local to define that region. But yeah, so the answer is in general we don't know. Okay, so I think I have maybe 5 minutes left, or let's see.
10 minutes.
Okay, 10 minutes. Yeah, thanks. Yeah. So I have so there's a few other things I want to say. Okay, the last part about evidence is, well, it's not really evidence, but it's some interesting comparison you can do with a free theory. Of course, that's always what we do, although we are not allowed to do that, but that's the only thing we know how to calculate. So there's some free theory calculation you can do, so you can't really do any quantitative comparison because it's not supposed to be holographic. But at least you see how this entropy, this restricted constrained entropy behaves. So let's think about one-dimensional chain of fermions, of Majorana fermions, let's say. Then if you make the hopping a little bit staggered, so you have a fermion that's Tij, Kij, something like that. Then if you make the hopping a little bit different between this and this, then this thing has a dispersion that's like a relativistic fermion. And then when the difference between, say, T even and T odd, when these two are the same, then this is gapless. Okay, so this is just a simple model for a Dirac fermion in 1 plus 1D with a mass. And then I want to consider a time-dependent situation, right? Otherwise, everything is trivial. So you can consider a quench where you start from a finite mass, which is T even minus T odd. You can start from a finite mass and you quench it to 0. So you start from the ground state of a massive theory, and then when you switch off the mass, you get a CFT, but with a finite energy state. So then entanglement entropy start to grow. Like for example, if you look at a region like this, then in a very long chain, the entropy will grow linearly because you create EPR pairs like this, and then it will stay there for some time, and then in a volume time, the EPR pairs will come back to itself. The entropy will go down again. Yeah. So for a region, your entropy basically looks like this. And this part is what is very different from the interacting theory. In the interacting theory, we expect to have thermalization, and it lasts for exponentially long time. But in the free theory, you get this part, which looks very similar. You have a high entropy, but then the later part is not chaotic, so it's different. So now we can study this. Here, we can study the behavior of this restricted entropy, of this constrained entropy in this case, where we have a, so my system is a circle. I'm drawing a line there. It's a circle, and then you choose regions like the same way we draw before. So, but we draw some smaller regions like A, B, C, something like that. So, okay, so you calculate that S of sigma BC. So the modular flow, the entropy as a function of the modular parameter little s. And then you see indeed in this quenched situation, because time, there is a time dependence, then indeed this minimum starts to deviate from 0. The deviation is small, but you see there is a deviation. Like in the time, if you don't have a quench, if you do this in the ground state, then you will see it's just symmetric and then minimum at the middle. There's a lot of oscillations, but if you track this, if you track, say, for example, delta S, which is like how much entropy you can reduce by doing the modular flow as a function of time, then after the quench, it starts to be non-zero, and then it has oscillations, and then it goes down. So this going down is because in this region, you have like the physics in this whole ABC region, there is a time where it looks like time independent. In the interacting system, this will happen for a long time. This is when you form a black hole, and then the black hole lasts for a long time. In this case, the only difference is it doesn't last very long. So if you look at time that's comparable with the system size, you'll start to see the currencies, a lot of oscillations. But qualitatively, the early time behavior is similar to what you expect in a collapse geometry. So roughly speaking, the comparison is like you have some matter collapse into a black hole, and then the black hole lasts for some long time. So you see this. You see that the HRT surfaces do not intersect each other after the quench. But then later, when the black hole forms and the geometry looks almost like time transition invariant, they will start to collide each other again. And there is also the simple feature that if you choose AB to have the same size as BC, then the minimal surfaces always cross each other because there is a symmetry. You don't know which way to go, one above the other or below. So in the case when AB is the same size as BC, this delta S is always 0, which is also confirmed in this numerics. Okay, so that's just saying that seems to be like qualitatively the same physics happens in the free case. Maybe I will just briefly write down what are other like open questions before I end. Sorry. That's scrambling is easy. Further discussion. Yeah, this chalk is very expensive. So sorry. Okay, one comment is about the relation to the entanglement purification that was mentioned earlier. So Tadashi and the collaborator has this proposal. Also, let's say if I look at AB, CD, then they define this quantity that's like finding the extremal surface that's minimal area, or that's extremal from here to this minimal surface. And that's due to, the proposal is that's due to entanglement of purification, which means you look for other states that reproduce the same density matrix rho AB, and then among those states, finding the minimal entropy for A and its purification partner. And that's the proposal. So from the tensor network point of view, the proposal is basically saying we want to find the state with the minimal entanglement entropy that reproduces the same rho AB, and the easiest choice is just remove the right half of the tensor network. You only leave these things here. And then the entanglement entropy of this will be given by that minimal area. Anyway, so there's something called entanglement of purification, which is determined by rho AB. Given rho AB, you can try different purification, minimize the entropy. And then there's correspondingly, you can define that for C. So clearly, we see, holographically, we see there is a relation to our quantity, which is the entanglement purification of A plus that of C. This plus that will be smaller or equal to our S tilde of BC. And I'm not completely sure whether this is true in general. It seems to be true if there is a superadditivity of the entanglement of purification, because this quantity is a minimization of the actual entanglement entropy for that sigma state. And if you calculate the entanglement purification for sigma, you get the same value. The modular flow does not change that. So, so you actually just need the fact that for every sigma this is true. Yeah?
Oh, wait, so maybe that was what you were just, I was just going to ask about that. For a fixed sigma, a fixed slice, you have this, if you find the minima, you find that you're maximizing over sigma separately on the two sides, so it's not clear you actually have the same quality, right?
And maxima. In this side, I don't need to maximize over sigma. The sigmas are obtained by modular flow. The modular flow preserves the.
Over big sigma. I mean, in the
Yeah, the big sigma. Mm-hmm.
Yeah, I mean.
Yeah, but they are required to attach to here.
It's just not completely obvious that in the maximization over the slice step, you're still respecting that inequality. I don't know.
I guess if you can show there always exists sigma that includes this and also that, then it should be okay, because for that sigma, you can show this is longer or equal to that. But that seems to be always possible, right? I mean, I can always have a sigma that includes this and this.
A maximizing sigma, not just any sigma.
I thought
Because you find some sigma, but if that's not the one that maximizes in your maximin, then you haven't got the right quantity. At least it seems like an issue. I don't know.
Only a local condition on sigma.
well, you can always find the sigma, let's say a sigma here join a sigma there, which include this and this. And then within that, you draw. I think it's okay, but sorry. So maybe the last thing to mention is you can generalize this quantity to multiple regions, which means you can think of something like multiple kinks, and then you do one modular flow, another modular flow, and then you get quantities with more than one restriction, and that seems to give you a way to probe more general surfaces in the bulk. Like you fix two anchor points rather than one or three. You can do it in multiple regions. And so in general, the message, I think in general, this quantity, although it looks like the definition is complicated, it's telling me something that generally a state cannot be described by a simple tensor network. And the reason why it cannot be described by a simple random tensor network is the description in terms of tensor network cannot be simultaneously optimized in different partitions. It means if I'm finding the minimal surface, I find a tensor network that optimizes the description this way, which means I describe the entanglement in terms of number of EPR pairs here. You cannot simultaneously do that in a different cut. And this modular flow, the fact that modular flow can disentangle is telling me that I cannot my description is not optimal. So by doing some modular flow here, I can make the description in the other direction. I can reduce that entanglement entropy. And one interesting thing it seems to also say is the modular flow, even in the case when the modular flow is not local, the modular flow knows something about time evolution in the bulk. Because when the bulk has time dependence, the HRT surfaces do not intersect, then the modular flow, although it's only a property of a state, it seems to know something about that. Thank you. I will stop here.